My name is Robert Zhang, and this is Johnny Wang. We are from Abingdon School, and we're working on the Matter from Light project. The Matter from Light project is basically, as the name says, matter from light. It's to try to prove the bright Whirler effect directly with the time detector. So if you have two high-energy photons colliding with each other, you make a positron and electron pair. What the experiment does is, this is overlapped. There's a front detector and there's a rear detector, and behind that there's a very strong magnet behind it. So any electron and positron that's produced from the experiment will be sucked into through the two time detectors. And what we are working on is we're working on 600 sets of data which we've obtained from the experimentation physicist who's actually done the experiment. And we've managed to find 3 different ways of analyzing the data, one of which isn't quite as successful as the other 2. Right. So this is the first way of doing the data analysis, energy analysis, where you compile many, many different sets of data together so that you can see a general trend in the energy which is detected on the time detectors. These graphs generally show you there's a higher energy in the front, and the energy kind of drop off afterwards. As I'm covering for a friend who's not currently here, in my opinion, this isn't quite a valid way of finding whether or not it's proven or not, because these sets of graphs are only made after that we know the experiment is actually running in these. So moving on to more effective techniques, my friend's going to talk to you about one of the programming ways of finding out how to do it.
Okay, so the photo on the left is the result of my program. And my program has 3 sorting algorithms. The first one is to sort all the data by the time of arrival, which is given in the data set. And then I used the optimum radius of 69 to draw a circle around each pixel on the front detector, which is about 20,000 of them, I think. Yeah, by calculating the energy of each pixel collisions and the contrasting with the back, we get a ratio. And if the ratio is below 0.5, then it means it's a positron. And if it's beyond 0.5, then it's a gamma ray.
Yeah. So the program he just described will be used on every single one of the 600 datasets, and depending on how many positron and electron pair you find in the end, you're going to decide whether or not this is actually one of the datasets where the experiment is running. And the other method, which is currently under development, is a purely statistical way of analyzing the data. Because there's a certain deviation of the 2 time detectors, we can't rely on the data 100%. So in a certain way, we can ignore the uncertainty which is produced by this experiment by finding the rate of change or something, which in this case is on the first detector, whenever there's a pixel that lights up, you draw a circle on the second detector and count how many of the pixels actually lit up on the second detector. And by changing the radius of it, increasing and decreasing it, you find an average for each set radius, what the average amount of pixels is lit up on there. You plot the graph of the number of collisions on the second time detector against the radius squared, because we don't want the exponential increase of the graph to be due to the exponential increase in the area we're finding. So this should theoretically give an exponential increasing graph. And on this graph, the point with the highest gradient should be the point at which where your increase in gradient causes all of the different differentiation of photon and electrons to be accounted for. So it pretty much negates the background radiation which could be picked up by the time detectors. And with the data we find, so the first graph is then applied to all 600 sets of data, and you get 1 point on each of these graphs. You find the numerical y value of these data points, and you plot them, the only points. You first number them numerically, depending on how big they are, space them out evenly on the second graph, and beyond a certain point on the second graph, you should have a straight line, which is an increase due to only background radiation. And before this point should be the sets of data which actually have the experiment running. So after we plot the second graph, we can then turn to the researchers at Imperial, and also Dr. Peter Hatfield, who's from Oxford. We can tell them that these sets of data out of the 600 are the ones where the experiment is actually running, and then we'll be able to prove to them that their experiment has worked, which is what we're fundamentally aiming for here. And this is our research project, Matter from Light.
Which agency sent up your chip to space?
Do you know?
What? How did you get your chip into space?
UK Space Agency. Yeah, it's UK.
With the UK Space Agency.
Thank you.
Pass that one along. Right, other questions about project and what they've gotten involved with? Yep, Will, excellent.
So for Lucid, you mentioned those sort of averages were per frame. Did you do like a calculation for a large amount of data, more than just one frame, the averages?
We used all the data that was on Tapas.
We used all of the data that was on Tapas. So for inside the South Atlantic anomaly, the averages of calculated from about 250,000 frames, whereas for outside the averages are from about 3.5 million frames. So it's a lot of data.
It did the code a pretty long runtime, but it did produce. It did give the code a pretty long runtime, but it did produce. It should produce accurate answers.
And then that's per frame.
What it gives out is the total number of alpha particles inside beta, gamma, etc. And it also gives the number of frames it's those have added up, and then we worked out the averages from that.
Right, good. Very well done. Thank you very much, teams.